Hello, my name is Krekora. This summer, I spent it studying the effect of heat treatment on the delta phase of niobium 310. My mentors were Dr. Peter Lee and Dr. Najib Chagor, and we found that this heat treatment could reduce the amount of delta phase present in niobium 310 subelements and also increase the hardness values. So to begin, superconductors are able to carry large amounts of electrical currents with no resistance. Our superconductor is used in the Large Hadron Collider at CERN, and these instruments are very expensive and precise, so we want to have a lot of control over them and the materials that are going into them. So we want to look at the phases within these materials, and what a phase basically refers to is the arrangement of elements composing that material. So it's called microstructure, and it's referring to the relative positioning of atoms. And in figure 1, we see the niobium 310 crystal in the A15 structure. A15 structure refers to 3 niobiums for every 1 tin. And so each phase has distinct material properties. So it could be ductile or brittle or hard depending on the way that the atoms are arranged. And in figure 2, we can see, oh, it's kind of bad, but in figure 2, we can see a sub-element that I was studying, and you can see the copper on the outside, and then this is the niobium phase, and this yellowish phase right here is alpha, and the blue one on the inside is delta, and that's what we'll be focusing on. And these black holes are just voids. And what we used were the restacked rod process niobium 3 wires, which were found by Dr. Chagor to be less brittle and more resilient to axial stress. And so what we're looking at is how to improve upon that. And so in our methods, we took 7 different niobium 310 species and put them in a furnace for 325 degrees Celsius for 99 hours. And then after that, we took the untreated and heat treated samples and metallographically prepared them for imaging. We used the DSX 1000 to take pictures, and then used Fiji to analyze and visually inspect the phase present in our samples. And then after that, we used the following equation and a VIX micro hardness tester to assess the hardness values for the pre and post niobium 310 samples. And so what we found is a reduction in all of the species. The heat treatment is very promising, and it is a lot more promising for these last 4 species, which had prior heat treatments when they were being made before the heat treatment that we did for 325 degrees Celsius. And these last 2 columns are the hardness values that I found. I put estimates like squiggly lines in front of them because I really didn't feel 100% confident in these values, but I feel like they are a good idea of where we are, and we can definitely see there is a definite increase in the hardness value. And so in conclusion, we found that this heat treatment increases the hardness value and decreases the delta phase found in these subelements. And so it can be used to improve the axial strength, and in addition to the RRP wires that Dr. Chagor found. And so moving forward, I definitely more hardness tests, find more specific fracture limits for the samples, try to find out the minimum amount of axial loading that will cause damage in the sample, because that was really what was wrong with niobium 310, is that it's super brittle, and literally any amount of axial loading will cause damage in it before the RRP. And after RRP, we kind of gave more wiggle room, and now we have even more. And so basically we want to go with longer heat treatments as well, because we've only done 99 hours, and we're looking forward to doing 200 and 400 hour treatments. And so my contact information is down here. Thank you all for your time. Thank you, Dr. Lee, Dr. Chagor, and Ms. Hughes for the RU.